This is Owen Lynch with Computer Algebra.
Cool.
So I'll hand it over to you.
Thanks. So this is Gatlab, Computer Algebra, and Standard ML modules combined. And let's get started. So this talk has 5 parts, and you're just gonna have to. I don't have section headers, so you're just gonna have to vibe when the parts actually shift. So I'm gonna start and talk a little bit about the general context of the Algebraic Julia organization, which is a GitHub organization that we have a lot of packages in. Gatlab is one of them. And then I'm going to say a little bit about the Topos Institute, where I work. Then I'm going to tell you, maybe give you a bit of a inclination as to why I have, why we developed Gatlab and what kind of problems it solves. Then I'm going to give a short review of GATs. So GAT stands for Generalized Algebraic Theory. In Rust, they also have a thing called GAT, but it's called Generalized Associated Types, which is a little bit confusing. But and then I'm going to give a bit of a tour of some cool features in Gatlab, and then finally talk about future work. Gatlab is a refactor of the internals of Catlab. So, in one sense, you know, the internals of Catlab is a package that has been around since 2018, and we pass all the tests for Catlab. So, in one sense, we're somewhat stable, but in another sense, we did this refactor to enable a lot of new features, and but the focus was like we didn't want to maintain 2 separate versions of the GAT infrastructure, so the focus was on like make the new infrastructure, make sure it's backwards compatible, and then start doing some new things with it. And we haven't done too many of the new things yet, but they're exciting. But we've actually never given a talk. Well, so this is the second talk on Gatlab. I gave another talk 3 weeks ago, but for like the 5 years that the GAT infrastructure in Gatlab has been around, we've never actually talked about it so much. So hopefully this should be interesting, because this has been a core part of the core package in Algebraic Julia for a while, but now we're sort of starting to take it more seriously. So Algebraic Julia is a GitHub organization. We have a website, algebraicjulia.org. It's an informal collaboration between many contributors. We don't have a legal status. But mainly it's the Topos Institute and James Fairbanks' lab at University of Florida. The general mission of Algebraic Julia is to build a computer algebra system for category theory-based modeling. I won't get too far into that, but basically, like, category theory is a branch of mathematics, and category theory helps us figure out abstractions that can work across different modeling paradigms. So, we do work in different domains like epidemiology or multiphysics or agent-based modeling, and we want to like sort of build abstractions for what does it mean to be a model, what does it mean to simulate a model, what does it mean to compose models, what does it mean to relate models that will sort of work between different modeling paradigms, so we can have a uniform interface and so we can reuse code. So I work for the Topos Institute. The Topos Institute is a registered nonprofit in Berkeley, California. We now, as of a week ago, also have an affiliate in the UK. And our mission is to shape technology for public benefit by advancing sciences of connection and integration. We do a lot of category theory, and part of Topos is developing the Algebraic Julia project. But we also do other things, which you can come find me and talk to me about them, but not in this talk. So why Gatlab? So the thesis of Gatlab is really that, you know, programming language research has been developing for, you know, years and years and years, but it seems like computer algebra systems are a little bit stuck in the past. Like for instance, I don't. So for instance, I want type systems. I don't want, like, you know, I have things that are more interesting than just numbers, right? So maybe I want to be symbolically working with matrices, but where the dimensions of the matrix are the dimensions of the matrix are symbolic, rather than having a matrix of symbolic numbers. Lexical scoping. This is a topic in, like, you know, this is a classic problem if you ever do compilers to do capture avoiding substitution, and when you just treat variables as symbols, this is quite tricky to do. But if you have a more advanced system for naming, for keeping track of variables, which we do in Gatlab, then you can make capture avoiding substitution much more principled. And then structs. We should be able to have composite types in our computer algebra system, and you should be able to, like, you know, take in a struct of structs for instead of for, like, when you have a big thing, and namespace things properly, etc. Lots of other things. So Gatlab is sort of what I think of as a test bed to try experiment with stuff like this. And there's a lot of prior work in this area, which I won't go into too far, but these slides will be up on my website. I'll post a link after the talk, and it'll be under the YouTube video, so you can click on these links at your leisure. I will highlight CAP. CAP is Categories in Programming. It's implemented in GAP, which is Categories, Algorithms, and Programming, Groups, Algorithms, and Programming. Mohammed Barakat wrote CAP. I didn't know about CAP until about maybe, I don't know, 3 or 4 months ago, and I'm like, and it does a lot of the things that we wanted to do, but a lot better. So happens. But I want to shout out to them, and Mohammed Barakat, who writes it, is very nice. So what is the core idea? So now we're going to get into Gatlab. The core idea behind Gatlab is that there's sort of a hidden unity between two different things, which are ML style modules, and if you don't know what that is, I'm about to explain it, and syntax trees. But so in standard ML or ocaml, if you've never seen it, so this is ocaml. Basically, this is saying that this is giving a module type, which is saying that a module of type semigroup must have a type T in it, and must have a function which takes in 2 elements of T and returns an element of T. This is just ocaml syntax for a 2-argument function. And now, so I can make a module which implements this signature, where T is set to int, and mapend is just plus. And I can sort of hack this into Julia. So one way, of course, would be to actually use Julia modules, but it's not very. Julia modules don't type propagate. The type of module is just module. So if I want to actually like make all of this run fast, I'm going to, instead of attaching all my functions to modules, I'm going to attach them to structs. So in this case, I'm going to have a zero field struct called plus semigroup, and then I can implement plus semigroup. I can implement mapn for plus semigroup, and that'll give x plus y. And the idea here is that this is telling me what the type parameter t is. And now I can make a function that is generic over the semigroup that I choose. And it takes in the semigroup as the first argument, and then some element here, and then it just doubles it. So if I pass in plus semigroup, then this will add these two, and if I have passed in times semigroup, then this will multiply those two. And we can we can model this mathematically by a thing called an algebraic theory. So an algebraic theory consists of a collection of type symbols, a collection of function symbols, each of which has a signature. So something like it has a bunch of sorts, which are the arguments, and then it returns a sort, of types. And then a collection of laws, which give equations. So this says, like, for all x1 in S1, blah, 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 xl and SL, this term, which involves these free variables, is equal to that term. And algebraic theories are part of a branch of math called universal algebra, which has a long history, but the most exciting part of that history is William Leverre's 1963 thesis, which I encourage you to check out. If you just search Leverre thesis, it'll come up. And so here's an example. The algebraic theory for monoids. Monoids are a theory which extends semigroups. It has a single sort T. It has a function symbol M, which was what we were calling mapend before, which takes two elements of T and returns a T. And then it has a function symbol E, which takes no elements and returns a T. And then we have these laws. So E is an identity with respect to M, and M is associative. So we can sort of translate that mathematical definition into Julia. So we can just make an extremely simple algebraic expression type. You have the head, which is supposed to be a function symbol. I'm using symbols here, even though I said I wanted to do proper lexical scoping, but this is just to fast and dirty approach to give you the idea. But so this is just like a very simple algebraic data type. Then I can give a signature, just has like a vector of arguments and then a return type. An equation has a context, which has a list of like the context has like symbol and what type that symbol is. So a variable and what type that variable is. And then two algebraic equations that I want to be equal. And then finally, an algebraic theory just has a set of symbols, a map from function symbol, a set of type signals, a map from function symbol to the type of that function symbol, and then a collection of equations. And and basically, in Gatlab, we have a macro to declare a significantly more advanced version of this, and it looks like this. So I declare T as a type, I declare some function symbols, and then I declare these axioms. And I get out a data structure. I also actually get out a module named theory monoid that has theorymonoid.m and theorymonoid.e as functions. And these are the functions that I'm going to overload when I make models of the theory of monoids. So what is a model of an algebraic theory? Well, a model of an algebraic theory with sort symbols, function symbols, and equations consists of a type for each sort symbol, and then a function for each function symbol that is of the correct function type, and such that when I take each of my equations and replace each of the function symbols with an actual function, and then do the universal quantification over the context, then the equation becomes true. So for instance, there's a model int plus of the theory of monoids, where I interpret t as the type of integers, I interpret m as plus and e as 0. But there's also for every little n, there's a model of the theory of monoids where which is the integers mod n. And there's also a model of the theory of monoids with strings and concatenation. Or you can do real numbers with min, or real numbers with max, or subsets with intersection or union. So this is what I was saying at the beginning. I want to move computer algebra not away from just real numbers to these sort of either richer or less restrictive theories that have interesting models that are not necessarily real numbers. For instance, in this case, I might be using real numbers, but maybe I want, if I'm doing like convex optimization, I want to do computer algebra with, instead of plus and times, I want to do computer algebra with min and plus, which doesn't form a ring, it forms a semi-ring. But I can do all sorts of algebraic simplifications there, and that's sort of an interesting thing that I might want to do in a computer algebra system. So what does it actually look like now to declare a model of a GAT in Gatlab? Well, so previously I showed sort of like zero field struct models, but there's nothing actually to stop you from putting actually interesting values in your model struct. So this is like a parameterized model, which is parameterized by the modulus. So I have a model of the theory of monoids, which is the integers mod n, and I get that n parameter there. And now I can declare the instance, and I'm actually doing theory of groups because I also want inverse. So you can see here when my implementation for I've sort of changed things up, but now I'm calling this dot instead of m. I'm going to use x plus y, but then mod out by the model.n. And now I can actually use this with model macro, which basically it's kind of like import using, or it's kind of like using. So this is like using z mod n e dot. What this does is it just wraps this in a let binding that binds e and dot to anonymous functions that pass in z mod n7 as its first argument. So those are algebraic theories. Oh geez, I'm not doing well on time at all. What are generalized algebraic theories? Well, it's kind of like an algebraic theory, except like I said at the beginning, it has dependent types. So what's an example of something that you might want to do with this? Well, like I said at the beginning, you might want matrices. You might want to do symbolic algebra over matrices, but where the dimensions of the matrices are also symbolic. And you can do that with Gatlab. You can declare some types. I'm declaring a type of dimensions, a type of scalar, and a type of matrices, which depends on two dimensions. And then I can write out the type of matrix multiplication, and note that here this n has to be equal to to that n. Maybe I should be using my mouse so that it's on the recording. Oh well. And so, but then for plus, they actually have to be the same dimensions. So that's cool. Let's keep going though. So how to work with GATs in general. So they're a bit of a hairy beast because if you want to type check that two GATs are equal, that might like two types being equal might mean that I'm checking the type parameters of those types, and the type parameters of those types are arbitrary terms. So I have to decide if those terms are equal, and I have to solve like a word problem to do that, and that is in general undecidable. So that is sad. But we won't give up. So first of all, we can conservatively type check. So we can say, according to, maybe if you like apply the laws of this theory, then I can prove that these two things are equal. But actually, I'm just going to reject your program unless they're equal without having to do any of that rewriting. Or maybe I have some limited rewriting. Or I can just derive runtime assertions from this. So like screw static type checking, but from this I can say, okay, well when I multiply matrices, now I have to check that their dimensions are equal at runtime. Or we can just use these as like a contract and derive property tests. So whenever I have a model, I can use the equations of this theory and just like maybe just try to generate a bunch of random elements and then check if the equations hold. So yeah, so that's sort of how we wiggle around this problem that type checking for GATs is undecidable. And so now I'm just going to go through a bunch of some cool features of Gatlab and then finally talk about future work. So one cool feature about Gatlab is that so when you do category theory, whenever you learn about a new thing, you always ask, well, is there a notion of morphism between these two things? And for GATs, there is. So basically, I can write a morphism from the theory of monoid. So the theory of arithmetic, this is like piano arithmetic. So I have like a function symbol for successor, a function symbol for plus, and a function symbol for times. And then I have these laws which say how successor interacts with plus and times. And now from my theory of monoids, I can go ahead and say, I'm going to make a map from theory of monoids to theory of arithmetic where I'm going to interpret the operation here as plus in piano arithmetic or as times. And what this allows me to do is if I have any model of the theory of arithmetic, which may use actually something other than the natural numbers, which may interpret, then I can pull that model back along the theory map and get a model of the theory of monoids. Some other things. So, Gatlab, Algebraic Julia, we want to do declarative modeling. So here's Gatlab being used for declarative modeling. So this is similar to, MTK, but you notice I have this parameter theory ring. So I can change the GAT that I'm working in, and that changes the kind of operations that I'm allowed to use in my models. So in the theory of ring, I can just use plus and times. If I could extend the theory of ring, maybe to add like sine and cosine, and then I could use sine and cosine. And this is useful for declarative modeling because I can know up front like what operations I have to support. So if I want to like move this cross language or compile it to a certain thing, I know up front the operations that I'm going to need. Yeah. So, and and it runs. You can get a little nice little spring with gravity attached running out of this. Now, and this is using undirected wiring diagrams out of the hood and resource shares. There's a paper for on that. This is work by Sophie Libkind. And so, okay, so now future work. So sort of the big fish for Gatlab development over the next couple of years is, or the next couple of months actually, is we want to use the typed computer algebra to do partial differential equations. And now there's a lot more types in partial differential equations than there are in ordinary differential equations, especially if you do them the way that we want to do them, which is with the discrete exterior calculus. So that's what the DEC in Decapode stands for. And this allows you to do all sorts of fun multi-physics problems. But I want to keep, and I want to do multi-domain, multi-scale, multi-physics. So I have multiple spaces, so I have to type a variable by like, is this a 2 form, a 1 form, whatever? What space does this live on, etc. I might have morphisms, smooth maps between the space. So for instance, I include a boundary into the space, which is like a 1D manifold and a 2D manifold. Anyway, so there's a lot of use for typed computer algebra in this setting. More future work is rewriting. I've actually implemented eGraphs twice for Gatlab. Each time they have been swamped and gone unmaintained by other features that I added to Gatlab. They've never really like caught on, and I have never really liked the design. But I have a design which I think I like now, which is that you put in a mutable eGraph. Well, anyway, I won't go into that. But it's a cool design. And future work is interoperability. I want to be able to interoperate between models that I write down in Julia and maybe some other programming languages. And the sort of closed world assumption of my expressions, like I was saying before, that I know statically, like, oh, okay, I'm working in the theory of rings. It's only plus and times. I'm working in the theory of rings plus trigonometric functions. It's only plus times cosine. That helps with moving cross language. And that's the end. So, yeah, thank you.
All right. Am I on? No. Okay. Let's see. Yeah, okay. Thank you very much for the talk. It was great. We have time. Well, we're sort of out of time, but this is the last talk here, so we do have time to do questions. But if you have somewhere else to be, we are over time, so you are free to leave. Oh, wow. By how close we are. Yeah.
Have you also been looking at real algebraic geometry? Is this somehow related to your work?
Is real algebraic geometry like is that like algebraic geometry with inequalities as well as equalities?
Yes, yes.
It's cool, but I have not been looking into it. Yeah, I mean, this is mostly focused on equalities, actually. Yeah.
Okay, so I was playing with this library 1 month ago, and I was looking into the ocaml-like modules part of it, and I wanted to encode queues in ocaml style with axioms. And then I encountered a problem that the algebraic specification for queues uses if statements, like when the queue is empty, then you return something different than when the queue is not empty. And maybe you have some idea how to properly encode those ifs in equations, because I can provide 2 different implementations of ifs and include them in the type of the module. but it looks ugly and it drowns in boilerplate, like if for returning elements and if for returning new queue from tail. It's not optimal. And do you have any idea how to properly encode it, or maybe you need to somehow extend the library?
Yeah, well, it seems like to me the thing that you would want for that is like optionals, right? Like, you know, union sum t nothing. And in order to do optionals, you need generic types and sum types, neither of which Gatlab supports. Because, well, because we haven't gotten around to it. I mean, it would be cool, but the thing about adding sum types is that it actually restricts the class of models that you can use. So it's like, you know, more features equals fewer modules, or fewer models. But in the context of like just using this as a module system for Julia, that definitely makes a lot of sense. So, yeah, it's a good. But maybe if you want that, just use ocaml.
Yeah.
Ocaml's great. I love ocaml.
I mean, there are so many languages out there that have like are equipped with better type systems to do this kind of things like Haskell or OCaml or
Yeah.
what drove you to do this in Julia?
Well. So there's a couple things. So one, you can do algebraic theories in OCaml. You can't do generalized algebraic theories because OCaml is not dependently typed. And I think generalized and the other thing is that really like what's going on here is it's not just a module system, it's also a computer algebra system. Like whenever you declare a theory, you don't just work with models of that theory, but you can also work with like syntax trees in the language of that theory. And sort of do rewriting like in Julia of syntax trees. And that's not so much of a thing that you can do. Like when you write down a model in OCaml, you don't also get syntax trees for that model, and you don't really get, and you don't have laws in OCaml, so it wouldn't make sense to like do egraph simplification on you know, the instances of that, and there's actually, it almost makes more sense to do GATs in specific as a computer algebra system, because in a computer algebra system, if you implement it with egraphs, you're sort of iteratively like figuring out new equalities via rewriting between your elements, and like via like finding new equalities, now terms might type check when they didn't before. So you know, you can say like, you know, the user puts something in, it doesn't type check, and you give out an error message like this doesn't type check, and the user can be like, oh, you need to apply this axiom, and the user says, okay, apply this axiom, and then two things unify, and then you try it again. Oh, now it type checks. So there's like a lot of, it's a different vibe.
That's what systems like Idris or some of these systems. You have I've heard of Idris, for example.
Yeah.
Where basically the implementation of your function is the proof of the theory that you. I don't know.
Yeah. No, I mean, I love Idris. But the idea of Gatlab is that, part of the idea of Gatlab is that sort of the expressions that make up Gatlab should be interoperable. I don't want to embed a entire Idris interpreter into JavaScript.
Was there one more question? Or that? Okay, we got all the questions.
Cool.
Thank you very much for the talk. Maybe last round of applause, and